So our project is the March Machine Learning Mania, which is to help us predict the 2025 March Mass results. So our motivation is that, like any kind of sports, the NCAA basketball tournament is notoriously difficult to predict, as there's tons of nuances, tons of different stats, and a lot of times these stats fall short in predicting outcomes. At the same time, there's a lot of data collected by various websites that can be used to help us gauge likelihood of teams winning. But as humans, it can be difficult to do this. So this is where neural networks can help us find those patterns to help us predict tournament winners. So our goal is to predict the winner of any given NCAA tournament game. And to do this, we're going to use historical data, including team stats, seeds, outcomes. And we're going to feed this into a neural network to learn patterns from these past matchups. And our main goal is to evaluate if the model can perform better than random or traditionally seed-based guesses, which is a very predictable form of guessing. So our dataset comes from Kaggle's March Madness Machine Learning Mania competition, which is a very robust data set. It has tons of data dating back to seasons early as 1985, with a lot of different info such as field goal percentages for winning and losing teams and other tournament data. So to evaluate our models, we used accuracy and area under the curve as metrics, and we also used a regression model and random selection as baselines for our project.
And we're with the random selection, there are two kind of baselines with that. One is pure random, which is going to be always a 50-50 between, as in it like predicts 50% one team, 50% other team for any given matchup, and then slight randomness where it takes in the seeding and the difference in seeding into account and uses past probabilities in that difference to randomly select a winner. That second model having about a 60 to 61% accuracy. Our first model that we wanted to use was an LSTM, and the reason we kind of went towards that was we felt that past games would maybe tell us a little bit more about the way a team performs and what it takes to win. It could also be a way to identify momentum. So take NC State's run last season where we had a massive swing in momentum and went from a team that wasn't going to make the tournament to a team going all the way to the Final Four. Our base LSTM architecture was used an LSTM layer followed by a fully connected hidden layer of 64 nodes, and then a sigmoid activation function to identify the winner. So if team 1 won, it was 1. If team 2 won, it was a 0. And then fed in game data from the regular season running up to these. To the tournament as sequences that we wanted to check against. And we used a varying level of the sequences. And we found this really interesting. The results proved to be very poor. And they proved to be poor regardless of the number of epochs and sequence links that we use. So we gave 3 examples up above of kind of early results we had seen. So stuff like having a sequence length of 5, so 5 previous games for a given for one or both for both given teams, with 10 epochs of training with the same sequence of larger amounts of epochs, and then an example of kind of like the medium sequence length for 40 with 35 epochs. And while it performs better than complete randomness, it underperforms even seed-based random selection, which surprised us in a long way. And something we had thought while seeing these results was that maybe the kind of the scale of the day and the these chains were misleading and weren't allowing us to encode something like momentum without an explicit flag or explicit variable for that. So to kind of check to see if, hey, maybe this is a lot simpler than the task is much simpler than it needs to be, we tested something quite a bit simpler and went with a MLP, a 3-layer MLP with a 22 node input layer, a 128 node hidden layer, and then 32 as a second hit layer, and then use the sigmoid activation function to get that output to a 1 or a 0. And we did this kind of in a really rote way where we looked at, say, okay, what does a person do when they create a bracket and they don't really know much about basketball? They look at the seeding and they look at the general stats of the teams. we encoded those things to see if something that simple could outperform these metrics, and ended up getting a really surprising result that it does perform the LSTM and performs both kinds of randomization. It's still not great. And that's something we had found earlier with some of the EDA, was that even with knowledge of stuff, even with things like close matchups, the the it didn't really matter what model you had. It's just a coin flip at a certain point. So take something like a 1 and 2 seed playing against each other. And so I guess with this model, some of the other stuff is we had performed some level hyper parameter optimization. So stuff like k-fold hyper parameter tuning with randomized search, and then k-fold cross validation to evaluate. But to kind of visualize kind of the results of that LLP, we had, this is the prediction accuracy by the seed difference. Oh, sorry, go ahead. Sorry, this is not on my slide.
Yep. So here, yeah, as we were going off here, you can see the difference between the seeds. So here we had to randomize the data here a little bit because the data was so clean that team 1 was always the winner versus team 2 being always the loser. So here we randomized it to be able to see how accurate it was in comparison to other teams. As you can see here for 12, it has a strong peak, which is something that we were not expecting, but it could be due to the fact that the data set that we have is also still limited due to the amount of years that we have collected. And we can see how accurate it is compared to the bigger gaps. So when it's team 1 versus team 2, we can see how we're more accurate in predicting that. But when it's a closer team between the seedings, like team 4 versus team 6 with a difference of 2, we can see how we're below 50%, as that's a harder seeding to predict. So here in the next slide, we can see here how the model results work for specific matchups. So 4 versus 12, 5 versus 6, 2 versus 4, and so forth. We could see how we have 100% accuracy. Because of this, we could say that we have a lot more data for this, because this is how seedings do kind of play out with the top seed versus the lower seed, compared to the very far extreme where the 2 seeds are quite random and nuanced. So team 12 versus team 12 would have to have a seed 12 team from 1/4 of the bracket go against another team 12 team from the other side of the bracket, and they have to make it to the final 4. So that would explain why there's so limited data that we would not have been able to predict. And everything in between, we could see how there is data, and the more often that the matchups happen, we do have a way to predict it. And as we could see for the first round, we could have way better accuracy than the random prediction.